Myself, Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Abhiday Namdar Senior College. Now, in the paper Groups and Coding Theory, we have seen first and second unit. Now, first unit was introduction. In second unit, we have seen definition of group and some examples of finite and infinite groups. Now, we start with the third unit, that is finite groups and subgroups. Now, these are the points that we have to cover in the third unit. Order of a group and order of an element. Then definition of subgroup, finite subgroup test, subgroups of Zn, some examples. Then what is the meaning of cyclic group, how to find generators of Zn, and permutation groups. Now, the first is order of a group. The number of elements of a group, finite or infinite, is called its order. So, if the group is finite, then easily we can count the number of elements in that group. So, that number is nothing but the order of group. Now, for order of group G, the notation is this, which is same as cardinality of some set, because order of group is nothing but cardinality of group itself. So it is cardinality or order of G, or O in round bracket G. Now the group Z6, it contains 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. It is a group with respect to addition modulo 6. Now this group contains 6 elements, hence order of Z6 is 6. Similarly, Z4 contains 4 elements, namely 0 bar, 1 bar, 2 bar, 3 bar. It is a group with respect to addition modulo 4. So in general, Zn forms a group with respect to addition modulo n, and it contains the elements 0 bar, 1 bar, 2 bar up to n minus 1 bar. So cardinality or order of Zn is equal to n. Now already we have seen that set G equal to 1 minus 1 I minus I is a group under complex multiplication. Now there are 4 elements in G, so order of G is equal to 4. Now U10 is 1379. This is also a group under multiplication modulo 10. It contains 4 elements, so order of U10 is equal to 4. Now, there are some groups which are not finite. For example, Z with respect to addition, Q with respect to addition, R with respect to addition. All these groups are infinite. So, we can say that all these groups have infinite order. Also, the group GL to R, general linear group of all 2 by 2 matrices under multiplication with non-zero determinant, has infinite order. Now, order of an element. Let G be a group and A is an element of G. The order of an element A is the smallest positive integer in such that A raised to n is equal to identity. If no such integer exists, then we say that A has an infinite order. See, here we are defining order of an element. Already in last unit, we have seen what is the meaning of integral power of some element. So, we have defined for n greater than 0, for n less than 0, and for n equal to 0. So what is order of an element? It is nothing but the smallest positive integer n, for which we are getting a to the power n, means a star a n times equal to identity of that group. And if no such integer exists, then in that case we say that that element has an infinite order. Now this is the notation for order of an element. Now always remember, order of identity element is 1, because if E is the identity element in a group G with respect to star, then E raised to 1 is always E, which is identity element. Actually, E to the power of any positive integer is identity, but according to definition, it is the smallest positive integer n, for which A raised to n is identity. So among all positive powers, 1 is the smallest one, for which E raised to 1 is identity. So order of identity element is 1, whatever is the group. Now see this example. Here we have to calculate order of every element in a group Z4, which is 0 bar, 1 bar, 2 bar, 3 bar with respect to addition modulo 4. Now in Zn with addition modulo n, 0 bar is always an identity. And just now we have seen order of identity element is 1. So directly we can write here order of 0 bar is 1. Now to find order of 1 bar, now we are using definition. Now to find order of 1 bar, we find the smallest positive integer n for which 1 bar to the power n is equal to identity, which is 0 bar. So what we do? We calculate 1 bar is to 1, 1 bar is to 2, 1 bar is to 3 like that till we get identity as answer. So 1 bar is to 1 is 1 bar, which is not identity 0 bar. So we consider next power of 1 bar. 1 bar is to 2. So it is 1 bar plus 1 bar 2 times because it is a group with addition modulo 4. Now 1 bar plus 1 bar is 2 bar. Again it is not 0 bar. So next power 1 bar raised to 3, which is 1 bar plus 1 bar plus 1 bar 3 times, which is 3 bar. Again not equal to 0 bar. So consider the next power 1 bar raised to 4, which is 1 bar plus 1 bar plus 1 bar plus 1 bar 4 times, which is 4 bar. But if we divide 4 by 4, we get 0 as the remainder. So 4 bar is same as 0 bar. So 1 bar raised to 4 I am getting as 0 bar. But I didn't get 1 bar raised to n equal to 0 bar before 4. It means 4 is the smallest positive integer for which 1 bar raised to 4 is 0 bar. So I can say that order of 1 bar is 4. Now, similarly to find order of 2 bar, we continuously calculate 2 bar raised to n till we get the answer as 0 bar, identity of Z4. Now, 2 bar raised to 1 is 2 bar, which is not identity. 2 bar raised to 2 is 2 bar plus 2 bar, which is 4 bar. And in Z4 it is 0 bar. So not necessary to calculate it further because we get 2 bar raised to 2 is 0 bar. So the smallest power is 2. Hence order of 2 bar is 2. Now next element is 3 bar. Again 3 bar raised to 1, 3 bar. 3 bar raised to 2 is 3 bar plus 3 bar, 6 bar. So it is equal to 2 bar because if we divide 6 by 4, the remainder is 2. But 2 bar is again not identity element. So calculate the next power. 3 bar raised to 3. So it is 3 bar plus 3 bar plus 3 bar, 9 bar. Now in therefore 9 bar is same as 1 bar. Again not identity element. Now 3 bar is to 4, which is 12 bar. But 12 bar is equal to 0 bar in Z4. So we get 4 as the smallest positive integer for which 3 bar is to 4 is 0 bar, an identity element. Hence order of 3 bar is 4. So in this way, by using definition, we can calculate the order of every element in the group. Now see one more example, because in previous example the operation defined on that group is nothing but addition modulo 4. Now here the operation is multiplication. Now find the order of each element of the multiplicative group 1 minus 1 I minus I. Now in multiplicative group 1 minus 1 I minus I, 1 is the identity element. So its order is directly 1. Now, to calculate order of remaining elements, we compute power of every element till we get answer as 1, which is identity element. Now see, minus 1 raised to 1 is minus 1, which is not identity. So calculate the next power of minus 1. Minus 1 raised to 2. Now as the operation here is multiplication, we consider minus 1 square as minus 1 into minus 1, which is plus 1, and it is the identity of group. So order of minus 1 is 2. Now next element is I. Now I to the power 1 is I, which is not identity. I to the power 2 is I multiplied by I, which is I square. And in complex number, I is square root of minus 1. So I square is minus 1, which is not identity element of that group. So we calculate next power I cube. Now I cube is I square into I, but I square is minus 1. So minus 1 into I, it is minus I, which is not again identity element. Now next is I raised to 4, which is I square into I square. But I square is minus 1. So minus 1 into minus 1, it is plus 1. So finally I to the power 4 we got as 1. So the smallest positive integer n for which I raised to n is 1 is 4. Hence order of I is 4. Now the last element minus I. In the same way, minus I to the power 1 is minus I, not identity. Minus I raised to 2 is minus I into minus I. Now minus minus it is plus and I into I is minus 1. Again not identity element. Minus I raised to 3 is minus I square into minus I. Now minus I square is minus 1 into minus I. So it is plus I. Next, minus I raised to 4 is minus I square into minus I square, which is minus 1 into minus 1 plus 1. So, order of minus I is 4. Now, see one example of infinite group. In Z with usual addition, the identity element is 0. So, order of 0 is 1. But if you consider suppose the element 2 of Z, then 2 raised to 1 is 2. 2 raised to 2, which is 2 plus 2, that is 4. 2 raised to 3, it is 2 plus 2 plus 2, 6. So, we never get 2 raised to n is equal to identity 0 for some positive integer n. So, order of 2 is infinite. Similarly, all other elements have infinite because by taking positive integral power we are not getting it equal to identity of that group, that is 0. So only identity element 0 has order 1 and all other elements have infinite order in Z with respect to addition. Now, this is one important theorem. Let G be a group and A is an element of G. Then A to the power n is identity of that group if and only if order of A divides n. So, by definition, order of A is the smallest positive integer for which we are getting the identity element. So, whatever is the order of A, it divides n if A to the power n is identity. And if A to the power n is identity, then order of A divides n. Now, subgroup. Now, we know already what is the meaning of subset. So, subset means what? We say that A is subset of B if every element of A is present in B. Then A is subset of B. Now, similar to subset, there is a concept of subgroup. So, already we have seen group. Now, we are define subgroup. See the definition. A non-empty subset H of a group G is called a subgroup of G star if H star is itself a group. That is, if H itself forms a group under the same operation of G. In this case, we write that H subgroup of G and we read this as H is a subgroup of G. Now see the definition. First of all, G with respect to star is one group. Now H to form a subgroup of G, H must be non-empty subset of G. And secondly, H with respect to star must form a group. That means whatever is the operation defined on that group G, with respect to same operation, H must form a group. And at the same time, H is non-empty subset of G. Then we say that H is a subgroup of G. Now, if you consider any group G with respect to star, then that group has always two subgroups. Now, one is the set containing identity only, that is singleton E, and another is G itself because every set is subset of itself. So, for any group G with identity E, singleton E and G are always subgroups of that group. These two groups are called as trivial or improper subgroups of G. Now, what is proper subgroup? The subgroup of G other than the trivial subgroup is called as proper subgroup. Now we have seen some examples. See, G equal to 1 minus 1 I minus I. It forms a group with respect to complex multiplication. Now in this case, 1 is identity element. So if I consider the set containing 1 only, that is singleton 1, and the set G itself, which is 1 minus 1 I minus I, then these are always subgroups of that group G equal to 1 minus 1 I minus I. So these two groups are trivial or improper subgroups of G. Now, if I consider the set containing 1 minus 1, then it is non-empty subset of 1 minus 1 I minus I, and it is itself a group with respect to complex multiplication. So we can say that 1 minus 1 is a proper subgroup of 1 minus 1 I minus I. Now, see, R forms a group under usual addition, means regular addition, R forms a group. Now, Z, that is set of integers, is a non-empty subset of R, and with respect to same addition, Z forms a group. Hence, we can say that Z with addition is a subgroup of R with addition. Similarly, the set of rational numbers Q is a non-empty subset of set of real numbers. Now, R with respect to addition forms a group, and with respect to same addition, Q also forms a group. Hence, we can say that Q with addition is a subgroup of R with addition. This example already we have seen that 1 minus 1 is a subgroup of 1 minus 1 I minus I under complex multiplication. Now, to show that some set H is a subgroup of G, or to check that H is a subgroup of G or not, there are some subgroup tests. Now, theorem 1. One-step subgroup test, that is necessary and sufficient condition for a subset to be a subgroup. Now see the statement. Let G star be a group and H be a non-empty subset of G. Then H is a subgroup of G if and only if A star B inverse is present in H for all AB belonging to H. Or a necessary and sufficient condition for a non-empty subset H of a group G star to be a subgroup of G is that AB in H implies A star B inverse belong to H. So whenever you have to show that H is a subgroup of G, first of all H must be non-empty subset of G, and secondly only one condition we have to check, that A star B inverse is present in H for all AB belonging to H. So as there is only one condition, this subgroup test is known as one-step subgroup test. Now see the remark. Even though the same name is one-step subgroup test, we have to actually follow the 3 steps given below. So first step is show that H is non-empty by verifying that E is present in H. Now in actually one-step subgroup test, we have to check A star B inverse is present in H or not. Now for that we consider two general elements AB in H, and then we check or show that A star B inverse is present in H. If all these conditions are satisfied, then by one step subgroup test we can say that H is a subgroup of G. Now let G be an abelian group with identity element E. Now here that group is not specified, it is any group which is an abelian group, means commutative group, and H equal to X in G, satisfying X square equal to identity. So H contains all those elements of group G whose second power is equal to identity element of that group G. So that H is a subgroup of G. So here we will use one-step subgroup test to prove that H is a subgroup of G. Now, as the members of H are from G only, clearly H is subset of G. Now, to show non-emptiness, we check the element E, whether it is present in H or not. Now, E is an identity element of G. So, E is present in G. Just we check this condition for X equal to E. Now, E square is identity because E is an identity element. So this condition is also satisfied by E. Hence E is present in H. So H is a non-empty subset of G. Now to check the condition, we take two elements A and B from H. Now, as A and B are present in H, by definition, A and B are elements of G satisfying this condition. So, X square equal to identity, that condition is satisfied by A and B both. So, we get A square is identity and B square is identity. Now, according to one-step subgroup test, we have to prove that A star B inverse, this element is present in H. Now, as A and B are elements of G, A star B inverse is an element of G because G is a group. So, only thing is A star B inverse bracket raised to 2 is equal to identity. That part we have to show. So, consider A star B inverse raised to 2. Now, by definition of integral power, it is A star B inverse star A star B inverse. Now, by using associativity of star, because G is a group, it is A star in bracket B inverse star A star B inverse. Now, as G is an abelian group, star is commutative. So, B inverse star A can be written as A star B inverse. Again, using associativity, we get this as A star B inverse star B inverse. Now, by definition of integral power, A star A is A raised to 2 star B inverse is B inverse raised to 2, which is A square star B square raised to minus 1. Now, as A and B are elements of H, A square is identity, B square is identity. So, this is E star E inverse and inverse of identity is itself. So, it is E star E, which is E. So, finally, we get A star B inverse raised to 2 is identity. So, A star B inverse is an element of H. Hence, H is a subgroup of G. Now, another way of showing H is a subgroup of G is two-step subgroup test. Let G star be a group. A non-empty subset H of G is a subgroup of G if and only if it satisfies following conditions. Now first is A star B is present in H for all AB in H, that is closure property. And secondly, A inverse belong to H for A in H, means inverse exists for every element in H. So whatever is the condition A star B inverse present in H, in one step subgroup test, it is splitted here. So first condition is A star B in H and secondly A inverse is in H. So there are two conditions. That's why this test is called as two-step subgroup test. Again, whenever by using two-step subgroup test, we check or show that H is a subgroup of G, then first you have to check for non-emptiness of H and H subset of G, and then we check for these two conditions. Now, one more test is there, that is finite subgroup test. Let H be a non-empty finite subset of a group G. If H is closed under the operation of G, that is A star B is present in H whenever A in H be in H, then H is a subgroup of G. Now, finite subgroup test is applicable only if H is a finite subset of some group G. Now, how to check for subgroup of G or not? If H is closed under the operation of G, that is A star B is present in H whenever AB belong to H, then H is a subgroup of G. Now, how to decide which test is applied? It depends on the problem. Whenever some set H is a finite subset of group, then definitely you can use finite subgroup test. Now see this example. Show that H is 1 minus 1 is a subgroup of G equal to 1 minus 1 I minus I under multiplication. Now here H contains only two elements. So H is finite subset of G. Hence we can apply finite subgroup test. Now clearly H is subset of G. At the same time H contains 1, so it is non-empty. So just we check for closure property. Now, to check for closure property, as it is a finite set, we prepare composition table as we have seen in unit 2. Now we write the members of H1 minus 1 as heading row and heading column, and the operation is multiplication. Now 1 into 1 is 1. 1 into minus 1 is minus 1. Minus 1 into 1 is minus 1, and minus 1 into minus 1 is plus 1. So observe the elements of this table. All are from H only. So we can say that H is closed under multiplication. Hence, by finite subgroup test, H is a subgroup of G. Now, second example. Prove that H equal to 0 bar, 4 bar, 8 bar is a subgroup of Z12 under addition modulo 12. Since H equal to 0 bar, 4 bar, 8 bar, again it is a finite subset of Z12. Z12 is 0 bar, 1 bar, 2 bar, 3 bar up to 11 bar containing 12 elements. So H is finite subset of Z12. Hence again we can apply finite subgroup test. So clearly H is a non-empty subset of Z12. So you can skip that step. Just take the closure property. So prepare the composition table for H. 0 bar, 4 bar, 8 bar in heading row and in heading column. Now on Z12 the operation is addition modulo 12. So using the same operation we prepare the composition table. So 0 bar plus 0 bar, 0 bar, 0 bar plus 4 bar, 4 bar, 0 bar plus 8 bar, 8 bar. As it is commutative directly you can write the column also. Now 4 bar plus 4 bar 8 bar. 4 bar plus 8 bar is 12 bar, which is 0 bar in Z12. So this element again 8 bar plus 4 bar is 0 bar by commutative property. And finally 8 bar plus 8 bar is 16 bar, which is 4 bar, because if we divide 16 by 12 then the remainder is 4. Now see these elements, all are from H only. So H is closed under addition modulo 12. Hence, by finite subgroup test, H is a subgroup of Z12. So actually finite subgroup test is very easy. So if H is finite subset of given group, then just prepare the composition table using the operation defined on that group, and then if it is closed with respect to that operation, then immediately you can say that H is a subgroup of that group. Now, these are some examples with infinite group. Prove that 2z equal to 2n, n in z is a subgroup of z with respect to addition. Now, here we cannot apply finite subgroup test because 2z is an infinite set. Now what is 2z? So it is 2 multiplied by n where n is in z. So we are multiplying all integers by 2. So z contains 0, 1, 2, 3 and so on, minus 1, minus 2, minus 3 and so on. Now multiplying every element of z by 2, we get 2 into 0, 0, then 2, 4, 6, 8 and so on, minus 2, minus 4, minus 6 and so on. So it is an infinite subset. So we are not applying finite subgroup test. So we can use either one step or two step subgroup test. Now we will use two step subgroup test. So clearly 2z is a non-empty subset of z as it contains 2 into 0 equal to 0 element. Now 2z is non-empty. Now next is closure property, that is for a comma b belonging to 2z, a star b, that is a plus b is again present in 2z. And then next is inverse property. So to prove closure property we will take two elements a and b from 2z, but every element of 2z is in the form of 2n, that is multiple of 2. So we can write a equal to 2m and b equal to 2n for some mn belonging to z. Now a star b is a plus b here because operation is addition. So a plus b equal to 2m plus 2n, which is 2 multiplied by m plus n. Now as m and n are integers, m plus n is again an integer. So it is in the form of 2 multiplied by some integer. So this is an element of 2z. So for any two elements a b in 2z, a plus b is again in 2z. So 2z is closed under addition. Now next property is inverse. So again consider one element a equal to 2m in 2z. Now we have to find inverse for a. That means which element should be added in A so that we get the identity element 0. Now it is 2m. So if you add 2 into minus m, which is an element of 2z in 2m, then we get 2m plus 2 into minus m is equal to 2 into m plus minus m, that is 2 into 0, which is 0, which is same as 2 into minus m plus 2 into m. So adding 2 into minus m in 2m, we get the identity element 0. So inverse is 2 into minus m for a equal to 2m. Thus inverse exists for every element of 2z. Hence 2z is a subgroup of z. Now next example is determine whether the given subsets are subgroups of a given group justified. Now till now we have seen the examples. In every case H was a subgroup of G, so that was show that type examples. Now here we have to decide whether H is a subgroup of G or not. So answer may be yes or no. So if it is not a subgroup, then we have to give why it is not a subgroup, that justification. And if it is a subgroup, then in that case using proper test, either one step or two step or finite subgroup, we have to show that H is a subgroup of given group. Now here in given group is nothing but G, and the set which we have to check for subgroup is nothing but H. Now first is H equal to 0 bar, 1 bar, 2 bar of additive group Z4. Means we have to decide H is a subgroup of Z4 with respect to addition modulo 4 or not. Now see here, H contains only 3 elements. That means H is a finite subset of Z4. Hence to check for subgroup, we use finite subgroup test. Now we prepare composition table for H with respect to addition modulo 4. So 0 bar plus 0 bar, 0 bar, here 1 bar, 2 bar. Then as addition modulo n is commutative, we get same column here. Then 1 bar plus 1 bar, 2 bar, 1 bar plus 2 bar, 3 bar, same here, and 2 bar plus 2 bar, 4 bar, which is 0 bar. Now observe that all elements are from, no, all elements are not from H, because if you observe here, there is 3 bar appearing, which is 2 bar plus 1 bar, 3 bar, and it is not present in H. And so H is not closed under addition modulo 4. Hence H is not a subgroup of Z4. So you have to observe carefully whether all elements are from H only or not. So 3 bar is present in Z4, but 3 bar is not present in H, and hence H is not subgroup of Z4. Now second is set of odd integers of additive group Z. Now odd integers means it contains 1, 3, 5, 7, 9, minus 1, minus 3, and so on. So H is an infinite subset of Z. So we cannot apply here one finite subgroup test. So either we have to use one step or two step subgroup test for checking. Now as 1 is present in H, H is non-empty and clearly it is subset of Z. Now for two-step subgroup test, first property is closure property. So we consider two elements from H. So let A and B are present in H. It means A and B both are odd integers. Now operation defined on Z is addition. So we add now A and B. Now A and B both are odd integers. So what is A plus B? See, you can take particular odd integers. Suppose A is 3 and B is equal to 5. Both are odd. Then what is A plus B? 3 plus 5 is 8, which is an even integer. So actually addition of any two odd integers is again a even integer. So A plus B is an even integer, and so A plus B is not present in H, as H is a set of odd integers. So addition of any two odd integers is not as odd integer we are getting. So closure property fails here. That is, it is not closed under addition. Hence H is not a subgroup of Z. As first property is not satisfied, we are not checking for inverse, because even though that property is satisfied, H is not a subgroup of Z. Now third, Q plus the set of positive rational numbers of R star, the multiplicative group of non-zero real numbers. Now Q plus is the set of positive rational numbers. That means it contains all those rational numbers which are greater than 0. So here we are not taking 0 and negative rational numbers. And R star is the set of non-zero real numbers. It is a group with respect to multiplication. Now we have to check whether Q plus is a subgroup of R star or not. Now Q plus is an infinite set, so we cannot use finite subgroup test. So again we apply two-step subgroup test. Now, as 1 is a positive rational number, 1 belong to Q plus. So, Q plus is non-empty and clearly Q plus is subset of R star. Now, first property is closure property. So, consider two elements from Q plus. Let A, B belong to Q plus. Now, the operation defined on R star is multiplication. So, A multiplied by B. Now, A and B both are positive rational numbers. So, their multiplication is again a positive rational. It means A into B is present in Q plus. So Q plus is closed under multiplication. So first property is satisfied here. Now second is inverse. So we consider one element A from Q plus. But as it is a positive rational number, it is in the form P divided by Q, where P and Q are integers, Q not equal to 0. Now in R star with multiplication, identity element is 1. So to find inverse of A, we have to find some element B such that A into B is equal to 1. For example, if it is 2 by 3, then 2 by 3 multiplied by which element is 1? So it is clearly 3 by 2. So for A equal to P by Q, in the same way there exists 1 upon A which is Q by P in Q plus such that A into 1 by A is 1, which is 1 by A into A. So for every element A equal to P by Q in Q plus, 1 upon A is inverse of A in Q plus. For example, if it is 5 by 7, then its inverse with respect to multiplication is 7 by 5. So in this way, every element in Q plus has inverse with respect to multiplication. So both the properties are satisfied. Hence, by two-step subgroup test, Q plus, that is set of positive rational numbers, is a subgroup of multiplicative group of non-zero real numbers. Now, one more example. This is actually very important to define the subgroup generated by A, from which cyclic group is defined. Let G be a group and A is an element of G. Show that H equal to A to the power n in Z forms a subgroup of G. Now here G is not a specific group, so just we consider G is a group with respect to some binary operation, say star. So as group is not specific, we don't know whether it is finite or infinite. So we cannot use finite subgroup test here to show that H is a subgroup of G. So we use again two-step subgroup test. Now first, H contains powers of A only and A is an element of G. So clearly H is subset of G. Now as A equal to A to the power 1, this element is in the form of A raised to n, where n is an integer. So clearly the element A equal to A raised to 1 is present in H. So H is non-empty. Now first property is closure property. So we consider two elements from H. Let A raised to m, A raised to n are members of H. Now, as G is general group, we are considering star as a binary operation on G. And with respect to that operation, we show that H is closed. So, consider A raised to m star A raised to n. So, A raised to m is A star A m times and A raised to n is A star A n times. So, it will be A to the power m plus n. So m plus n is again an integer. So by definition of set H, this is an element of H. So H is closed under star. Now second property is inverse. Consider one element A raised to m in H. Then A raised to m raised to minus 1 is equal to A raised to minus m. which is an element of H again, because the power of A is again an integer. So every element in H has inverse also. Hence, by two-step subgroup test, H is a subgroup of G. So what is this subgroup actually? The subgroup A raised to n in Z is called as the subgroup generated by A and is denoted by this symbol, as it contains all integral powers of A, like A raised to 1, A raised to 2, A raised to 3 and so on, A raised to 0, A raised to minus 1, A raised to minus 2 and so on. So the subgroup which contains A to the power n in Z is nothing but the subgroup generated by A. Now see the next example. Find all subgroups of Z12 with respect to addition modulo 12. Now see, Z12 contains the elements 0 bar, 1 bar, 2 bar up to 11 bar. So which are 12 in number. Now for every group G with respect to star, there are always two subgroups. One is the identity element only and another is group itself. So these are improper subgroups. So first we write the improper subgroups of Z12. Now in Z12 with respect to addition modulo 12, 0 bar is the identity element. So H1 equal to singleton 0 bar and H2 equal to Z12 itself. These are always subgroups which are improper subgroups of Z12. Now using the previous example, now we find subgroup generated by each element of Z12. Now we know that A to the power n is A plus A n times. But here it is addition, so a plus a n times is nothing but n multiplied by a. Now we start with the second element, as first element is 0 bar, which is identity, and 0 bar raised to n is again 0 bar for any n. So consider a equal to 1 bar. Now we find powers of 1 bar continuously till we get the identity element 0 bar. So 1 bar is to 1 is 1 bar. Now 1 bar is to 2 is 1 bar plus 1 bar, as the operation is addition, which is 2 bar. Similarly, 1 bar is to 3 is 3 bar, 1 bar is to 4 is 4 bar, 1 bar is to 5 is 5 bar and so on. 1 bar is to 11 is 11 bar. And when we calculate 1 bar is to 12, it is 12 bar, which is equal to 0 bar in Z12. Now why we are stopping this procedure here? Because if you consider 1 bar is to 13, then it will be 13 bar. 13 bar is same as 1 bar. If I consider next power 1 bar is to 14, it will be 14 bar, which is same as 2 bar. So what we are getting? We are getting again the same answers. It means here cycle gets completed. So from 1 bar is to 1 to 1 bar is to 12, continuously we are getting the answers which are different. But after getting 0 bar, if you consider the next powers, then you will get the same answers in the order. So what are the different elements by considering the power 1 bar is to n we are getting here? We are getting 0 bar, 1 bar, 2 bar up to 11 bar. So this set is complete Z12. So what is the subgroup generated by 1 bar? It is entire group Z12. Similarly, we find a subgroup generated by 2 bar. Now again find the powers of 2 bar till we get 0 bar. So 2 bar is to 1 is 2 bar, 2 bar is to 2 is 2 bar plus 2 bar, 4 bar. 2 bar is to 3 is 2 bar plus 2 bar plus 2 bar, 6 bar. So 2 bar is to 4 is 8 bar, 2 bar is to 5 is 10 bar, then 2 bar is to 6 is 2 bar, 2 bar, 2 bar, 6 times. It is 12 bar, which is 0 bar. So we got 0 bar here. So we stop that procedure. Now what are the different elements we are getting by taking 2 bar is to n? It is 2 bar, 4 bar, then 6 bar, 8 bar, 10 bar and 0 bar. So form one set containing these elements. So this is nothing but the subgroup generated by 2 bar. We call it next subgroup as H3. Similarly, we can find a subgroup for every element. So subgroup generated by 3 bar. It is 3 bar, 6 bar, 9 bar and 12 bar, which is 0 bar. And this subgroup and subgroup generated by 9 bar are same. Similarly, subgroup generated by 4 bar and 8 bar is 4 bar, 8 bar, 0 bar. Subgroup generated by 6 bar is 6 bar, 0 bar. Subgroup generated by 2 bar and 10 bar is same. And subgroup generated by 5 bar, 7 bar, 11 bar are same. So we are getting as H1, then H2, H3, H4, H5, H6. These are the subgroups of Z12 because some of the subgroups are same. So we are getting these subgroups which are distinct subgroups of Z12. Now next theorem, which is very important theorem. Intersection of any two subgroups of a group is again a subgroup. In other words, if H and K are subgroups of a group G, then H intersection K is also a subgroup of G. Now again, here G is any group with respect to say star. H and K are any subgroups of G, then their intersection, that is set of all common elements of H and K, is always a subgroup of G. Let H and K be two subgroups of G. Now to show that H intersection K is a subgroup of G, we use one-step subgroup test. Now first of all, H intersection K must be non-empty subset of G. See, H and K are subgroups of G. So H is subset of G, K is also subset of G. So H intersection K is again a subset of G. Now which elements are definitely present in H and K? Identity. Because they are subgroups of G, it means they are groups. So in every group, identity element is present and it is unique. So whatever is the identity element of G, same is the identity element of H and K. So E is present in H, E is present in K, which is identity element of G. So E is present in both the sets, H intersection K. So H intersection K is non-empty. Now we consider two elements A and B from H intersection K. And we have to show A star B inverse is present in H intersection K. Now AB belong to H intersection K implies A and B are present in H and A and B are present in K because intersection contains common elements. So A and B are present in H as well as in K. Now see, H and K are subgroups of group G. So again using one-step subgroup test in reverse way, because whenever H is a subgroup of G, then in that case for AB in H, A star B inverse is present in H. So we get here for AB in H and AB in K, A star B inverse is in H and A star B inverse is in K by using one-step subgroup test. Now as A star B inverse is present in both the sets H and K, we get A star B inverse is present in H intersection K. So we have started with A and B as arbitrary element of H intersection K, and finally we got A star B inverse is present in H intersection K. So by one-step subgroup test, H intersection K is a subgroup of G. Now, even though intersection of two subgroups is a subgroup of that group, it is not necessary that union is again a subgroup. So here the question can be asked in this way. Illustrate with an example that union of two subgroups is not a subgroup. Or the question can be asked as show that the union of two subgroups need not be a subgroup. So in this case we have to give an example in which H and K both are subgroups of that group, but H union K is not subgroup of G. Now we have seen that Z with respect to addition is a group. Now we consider its two subgroups and show that their union is not a subgroup. Now H equal to 2Z. So it is 2M M in Z. That is all the elements in Z multiplied by 2. So 2 into 0, 2 into 1, 2 into 2 and so on, 2 into minus 1. So we are multiplying every integer by 2. Whatever is the set is H. Similarly, K equal to 3Z, which is 3n n in Z. So multiply every element of Z by 3. So the set will be 3 into 0, 3 into 1, 3 into 2, 3 into minus 1, 3 into minus 2 and so on. So these two sets are subgroups of Z with respect to addition. Now, what is H union K? H union K is the set of all elements which are either in H or in K. Now, H contains all elements which are multiples of 2. K contains all elements which are multiples of 3. So, H union K contains all elements which are multiples of 2 as well as all elements which are multiples of 3. So 2 is present in H because 2 is 2 into 1. Same way 3 is present in K because 3 is 3 into 1. But 2 plus 3 is 5, which is not in H union K. That means even though 2 and 3 are present in H union K, as they are present in H and K respectively, their addition 2 plus 3 is 5 is not present in H union K. So H union K is not closed under addition. Hence we can say that H union K is not subgroup of Z with respect to addition. So remember this example that in Z with respect to addition, H and K are subgroups of Z plus, but their union is not a subgroup. Now, next theorem is every subgroup of an abelian group is abelian. Now, abelian group means group together with a commutative property. So, if you consider any subgroup of abelian group, then it is abelian. So, we consider G as an abelian group and H as any proper subgroup of G. Why we are considering proper subgroup? Because if it is a improper subgroup, then it is obvious, because improper means either H is G or H contains only identity element. So both are trivially abelian. So consider H as any proper subgroup of G. Now to prove commutative property, we consider two elements A and B from H. Now as H is a subgroup of G, H is subset of G. So AB in H implies AB is present in G. But the group G is abelian group. So for AB in G, A star B and B star A are same. That means for AB in H, finally we got A star B equal to B star A. So H is abelian as commutative property is satisfied by elements of H.